Doppler effect, question 2. The mean wavelength of an emission line of sodium is 589.3 nanometers when measured in the lab. The same line is observed coming from a distant star, but at a wavelength of 589.5 nanometers. Part A is the star approaching or receding, and explain. Well, with 1 mark, you're not going to get a mark for saying approaching or receding, it will be for the explanation. The wavelength has gone from 589.3 nanometers to 589.5 nanometers, a longer wavelength showing the light has been redshifted, so the star is moving away. So the star is receding, we have an increased wavelength, or the light is redshifted. Part B, calculate the frequency difference between the two sources, for 3 marks. Well, the datasheet tells us that wave speed equals frequency times wavelength, and we can rearrange this to give frequency is equal to wave speed divided by wavelength. For frequency 1, for the wavelength in the lab, the speed of light is 3 times 10 to the 8 meters per second, also given on the datasheet, and the wavelength was 589.3 nanometers, being 10 to the minus 9. This gives frequency 1 of 5.091 times 10 to the 14 Hertz. Frequency 2, putting in the speed of light again, and 589.5 nanometers, has a frequency of 5.089 times 10 to the 14 Hertz. We do have to go to several decimal places to be able to show a difference here. It's a very slight difference. The change in frequency will be the bigger number minus the small number. Don't forget the times 10 to the 14, giving a difference in frequency of 2 times 10 to the 11 Hertz. Make sure we put the units in at this point. Part C, calculate the speed of the star relative to Earth, for 2 marks. Well, the datasheet gives us the equation we need of change in frequency divided by stationary frequency is equal to speed of object emitting the light divided by the speed of light in a vacuum. This applies as long as the speed is much less than the speed of light, which it will be in this case. Rearranging for V, it equals the speed of light times the change in frequency over the actual frequency. Putting in the numbers, 3 times 10 to the 8 meters per second for the speed of light. The change in frequency, 2 times 10 to the 11 Hertz, we found in part B here, and the frequency in the lab we found here as frequency 1 of 5.091 times 10 to the 14, which gives a recession speed of 117,855 meters per second. Part D, describe how the analysis of the light would be carried out, including stating the apparatus used and the measurements made, for 4 marks, so we're looking for 4 good points here. Well, the light would be gathered using a telescope, sent through a diffraction grating. We would measure the diffraction angle and then calculate the wavelength using the equation wavelength equals d sine theta over n, where d is the gap between the lines on the diffraction grating, theta is the angle of diffraction, and n is the order of the diffraction line. Finally, part E. Using a value for the Hubble constant of 65 kilometers per second per megaparsec, calculate the distance of the star from Earth in megaparsecs, for 2 marks. Well, again, the equation we need is given on the datasheet, v equals hd, where v is the recession speed of the body we're looking at, h the Hubble constant, and d the distance of the object from us. Rearranging for d, it's equal to v over h. Putting in the numbers, we have a recession velocity of 118 kilometers per second, and we have Hubble's constant of 65 kilometers per second per megaparsec. giving a distance to the object of 1.8 megaparsecs.